Hello, class. This is a recorded lecture for section 8.4, and hopefully the last one for the semester. But this will talk about this idea of multiplicated inverse for matrices. They just call them matrix inverses, but it's actually the multiplicative inverse for matrices. So as we talked about inverses, we had an additive inverse where we just changed the signs of the matrix. And when you add them together, you get the additive identity, which are a matrix filled with all zeros. So now we're looking for the multiplicative identity. And that in our numbers is the number one, right? Where one times any number equals that. And the inverse would be the idea of flipping it for a fraction. So again, just to refresh your memory, the number one is the multiplicative identity. And right, 5 times 1 equals 5. So how do we find the multiplicative inverse for the number 5? It'd be 5 times, say, variable x equals 1. And so how would you do this? Well, it would be the flip of it, right? This is 5 over 1. So x would be 1 over 5. And so when you multiply those together, you get your multiplicative identity, which is 1. And so what we need to do now is figure out, first of all, before we can figure out what the matrix inverse is in the multiplication world, we need to define what the identity is. And the multiplicative identity for matrices is called the identity matrix. And it only occurs when we have a square matrix. And the idea is that on the diagonal, there's the number 1, and everywhere else you have 0. And so let me show you what we mean by that. Let's just take a 2 by 2 matrix, and we're going to focus on 2 by 2s for a while. So this would be the identity of a 2 by 2, where we have it, the ones on the diagonal and zeros everywhere else. Just to show you a 3 by 3, because it's a little bit easier to see the diagonals when you have more, right? This would be 0, 0, 1. So you could see everywhere is 0, and the diagonals have the 1. So say like you take any matrix, and let's take, say, the number 2, 3, 0, and 5. So when you multiply this matrix by the identity, and it doesn't matter what side you do it. If we call this matrix A and this matrix I, by our definition, you'll see A times I equals I times A. Now let me just show you how you calculate that again. A little bit review here of multiplication. So it'd be first row times first column, and you'd see that's 2 times 1 plus 3 times 0. And then second row, column 1 is 0 times 0. Whoops, excuse me. 0 times 1, and then plus 5 times 0. And then column 2, row 1 would be 2 times 0, and plus 3 times 1. And then column 2, row 2 would be 0 times 0, and then 5 plus 1. And if you see, you add these up, and I'll just put it in a different color. This would be 2 plus 0. This would be 0 plus 3. This would be 0 plus 5, or 0 plus 0. And this would be 0 plus 5. And so you could see that if you did that, we get back the same matrix that we started. And so that is the definite definition of the identity for multiplication. So when we talk about finding inverse, here's what we're looking for. So if you wanted the inverse of A, and typically you'll call it A with the -1 on the top. That's always going to equal the identity matrix, just like we were doing in the multiplication, where you always want that number to be equal to 1. Here you'll see that it'll always equal the identity matrix. And so the question is, how do you find these identities? There are a couple ways. We're going to start with the most tedious way and work our way when we talk about Cramer's rule and determinants. We'll also explain that way as well. So say like we take matrix A, and I'm going to define matrix A as 1, 4, 3, and 6. And one way to find the A inverse is to do what we call this idea of an augmented matrix. And so let's take a look at what that would be. So say like we start with 1, 4, you know what? This is not the matrix I have in my notes. So let's just erase that. I have the capability of erasing that. How about if we put in, this is what I have in my notes, 3, 5, 4, and 7. So now if you're looking to find the inverse, the idea is you do this augmented matrix, and we're going to do this row elimination technique that we did in the previous section. So the augmented matrix looks like this: 3, 5, 4, and 7. And then you're going to do the augmented matrix of the identity. And the strategy is to make the A matrix look like the identity, and what's left would be the inverse. So the strategy is eventually you want it to look like this: 1, 1, 0, 0, and you would have 4 numbers here. I call them A, B, C, and D. And then this matrix A, B, C, and D is going to be the inverse. And so how do we do that calculation? Well, it's exactly like we did it in the previous section, the kind of elimination technique. And so what do we want to do first? And unfortunately in this, you're going to end up with some fractions sometimes. So that's why I ended up picking this one. It has a little bit of fractions to deal with. So let's walk through this. So the first thing you want to do is to make this the number 1, where the 3 is. So how do you do it? Well, you multiply that first row by 1/3. And so if you do that, you get 3 divided by 3 is 1. 4 divided by 3 is 4/3. And then we have 1/3. 0 divided by 3 is 0. That's nice. So we didn't do anything to row 2, right? So the next step is we want this to go to 0, right? We want this 5 to end up going to 0. So how do we do that? Well, what you're going to do is you're going to take the row 1 that we just did now, right? And multiply it by -5. And when you do that, you get what? You get 5, and then you would get 20/3. You would get 5/3, and you would get 0. And now we need to change the signs because we need to do the minus. Sorry about that. That's -5. So those all are minus. And now you add it to row 2. So we're going to add it to row 2 to get rid of to get our new row 2. And let's do that in a different color. So 5 and -5, that would be 0. So what's 7? So here's where it gets a little complicated, right? Well, 7 would be 21/3 to find a common denominator. And so that would be 1/3. So this would be 1/3. So then 0 and minus 5/3, that's nice. That would be minus 5/3. And then the last one would be 1 plus 0, and that gives us 1. Okay, so now we're in good shape with regards to this being 0 and this being 1. So now we have our first column taken care of. So now we need our second column that we have to take care of that. And so how do we take care of our second column? Well, to take care of our second column, first thing we would want to do is say, we need to make this number the number 1, right? So if we want to do that, what do we multiply row 2 by? Let's multiply it by the number 3, and that turns that back into number 1. So what we're going to do down here is the row 2, we're going to multiply it by 3. So what would that give us? 0. That gives us 1. So that's perfect. That bottom is perfect. And then minus 5/3 times 3 is minus 5. And 3 times 1 gives us 3. So how do we make this a 0? Well, if we do that, you would take this new row 2 and multiply it by minus 4/3. So what happens when we do that? Well, if we take the new row 2 that we just did here and multiply it by minus 4/3, what do we get? So we would get 0 minus 4/3. If we do this, that would be 20/3. And if we do that here, that would be minus 4. And so now we'll take this row and add it to row 1 to finish our calculation. So 1 and 0 gives us 1. Minus 4/3 and plus 4/3 gives us 0. Okay, so now our identity matrix is where our original matrix is, so we're in good shape. So 20/3 plus 1/3 is 21/3, so that's the number 7. And then we have 0 and 4 together, you get minus 4. So if you look at this, you would see that the inverse of a 0 is 7 minus 4 minus 5 and 3. And so I will let you do this if you're interested. I'll never know if anybody does it, but if you did this, a times minus a or minus a times a, or the inverse, will always equal the identity matrix I. And so as I always do on Brightspace, I will upload this presentation, but it walks through the calculation with the augmented matrix that we just did here. And it's a little bit better with regards to notes and my little whiteboard. I had to erase a few things as well. And so we do have a little bit, some matrices will not have inverses. And if that's the case, it's called a singular matrix. And I think the good news is that a lot of your fancy calculators will find the inverse for you. I would recommend learning how to do this by hand, especially with the 2x2. And 3x3s are more tedious, and I won't ask you to do anything bigger than that. So this idea of a singular matrix, again, if you end up getting an error, if you try to find that on your calculator with regards to that. And so when we take a look, for example, we could write a matrix equation that looks like this. If we have, where did it go? Here we go. If we have this matrix, we would find that we could do the coefficients, and you could see that if you have 3 equations, 3 unknowns, it's going to be a 3x3 matrix. You have 4 equations, 4 unknowns, etc. And then here are our variables. And we remember when we did the augmented matrix, we left the variables out, and you don't put them in if you're a computer. And you could see the equal sign ended up being that line with the augmented matrix, right? And then here's our answer. And then one of the other ways that you could do to solve this, and again, that's one things that computers will do, is that we'll set up the matrices that look like this. The A matrix is the coefficients of each one of the variables in our three equations. The X variable would be what, or the X matrix, excuse me, would be the three variables. And the B matrix here would be, the B matrix here would be the answers. Sorry. Okay, resuming. So one of the other solution ways of solving the system of equations is finding the inverse of matrix A. So let's define the inverse of matrix A like we have been doing as A to the minus 1, meaning the inverse. So if you take this equation and multiply it by the inverse of both sides of this equation, you would look like this. And it's important to make sure that you put it up on the what we would call correct side of the equation. Because remember, B times A inverse isn't the same as A times B inverse. So you always want to put it to the left side. That is it. And so if you do that, A inverse times A is the identity matrix I. And so we would have A inverse B. And remember, I times any matrix is what? It would just be that matrix. So this is how you could solve it as well. Computers like calculating inverses. So you could definitely do that. So let me show you what we made. So let me just show you this on the slide here because we just calculated this inverse, right? So let's look at it. So say like we had equations that look like this, 3, 4, 5, and 7, right? And that was the inverse that we just calculated. And if you find that inverse would be 7 minus 4 minus 5 and 3. So remember when we started with this and then we found the inverse. So if you think about that, okay, I put it on pause there as I decided that it's worthwhile to do this on the whiteboard. So I put up the slide up here on the whiteboard where here's our two system of equations. And you could see that if we set it up like we showed, we would have matrix A, which is the coefficients, times X, which are the two variables, equals the answer, the B matrix, 5 and 9. And so in our previous example, I took that coefficient matrix and found its inverse. So how do you find one of the solutions? Well, we set that up from the previous discussion we had, that it would look like A inverse times matrix B. So let's do that one. That's good practice here. So 7 minus 4 minus 5 and 3. And we're going to multiply it by 5 and 9. So this is a 2 by 2, and this is a 2 by 1. So you see these are equal. So we actually can do the multiplication. And what are we going to get? Another 2 by 1, which will be the X matrix. So let's see what the first one is. So that would be 7 times 5 and plus minus 4 times 9. So first row, and obviously we only have one column. And the next one would be minus 5 times 5 plus 3 times 9. So if we add those together, we should get the top variable will be the X. So this would be 35 minus 36. So that would be minus 1. And this would be minus 25 plus 27. And that would be 2. So again, we define x equals minus 1 and y equals 2. So show you another way to solve a system of equations. This is using the idea of multiplicative inverses of matrices. And this is an example of a 2x2. So we've showed you 3 techniques. And we're going to do one more in section 8.3. I kind of went out of order a little bit. And we're going to show you Kramer's method of calculating a system of equations as well using matrices. So that ends the recorded lecture for this section and section 8.4 in our textbook.